this presentation, I'm going to give you an overview of what we're going to cover for week 2. And basically for this week, we're going to learn the necessary information to address future topics. And this requires us to understand 2 topics specifically, and that is a binomial random variable and a normal random variable. So I want us to first go back to that first concept map we looked at last week. And here you can see how probability theory is used, or the random variable is implemented using probability theory. And that's sort of what we're going to focus on this week. So what I want to do is I want to zoom in on that concept map and look more specifically at the random variable. And what you can see is we have 2 basic options. We have, or 2 types of random variables. First, we have this discrete random variable, and then we have a continuous random variable. And as such, they can be represented differently. So a continuous random variable is usually represented through a probability density function, whereas the discrete random variable is usually represented using the probability mass function. And we're going to learn more about the probability mass function later on. We also know that a discrete random variable is binomial, and whereas a continuous is normal. So the first thing I want to cover is the binomial random variable. So as I stated already, the binomial random variable is discrete. So what is it? What do I mean by discrete? And again, this means that it's a specific integer, so it's not continuous. And in order to represent the binomial random variable, we create these functions called probability mass functions. And essentially, these functions describe the probability that the random variable will take a specific integer value. So let me show you what a probability mass function looks like. So a probability mass function looks kind of like this. And as you can see, it's not continuous, so this would be continuous, right? So it's not continuous, but instead you have individual discrete values, so individual integer values. So each bar specifically represents the probability of the random variable x, which is this large X, will be at any specific point. So for example, let's choose 1 bar. So basically, we would represent, if we were looking for the probability, we would denote it as the probability of x, and let's say we're going to choose bar 8 is equal to 8. And so when we go and we calculate probability using the probability mass function for a binomial random variable, we will solve for the probability of that specific integer. So what I want you to see here is that the binomial random variable is essentially the probability that a particular outcome occurs a given number of times in a sequence of identical and independent experiments. So for that probability of x equals 8, for example, we could say that it represents, or we're looking for a probability associated with the number of times something happens over 8, or happens 8 times. So for example, if we were going to conduct an experiment of whether or not a cheap set of tires will fail after 10,000 miles, a binomial random variable will give a probability for, in our case, 8 sets of tires failing after 10,000 miles. So this week, we are essentially going to learn how to compute the probability mass function for binomial random variable, and then we're going to use that essentially to recreate the graph above and calculate probabilities. The second type of random variable we're going to cover is the normal random variable. And the normal random variable is continuous. So again, it's different than the binomial random variable because those are discrete integers and this instead is continuous. So what I want to do is I want to show you something a little more specific about the normal random variable, because a lot of what we do in statistics is associated with a binomial random variable. In fact, the majority of theory underlying statistics and the sort of extrapolations that are very common assume a normal random variable. So we are going to essentially learn how to, again, compute probabilities, but in this case for the normal random variable. So again, you can see here that we have the probability distribution function, and we essentially use the probability distribution function kind of in conjunction with the cumulative distribution function to solve for probabilities at different points. So what do I mean by that? So we essentially can compute probability if we know certain values of x. So for example, let's say we want to solve for the probability of, or this probability, or this probability, or this probability, and we do all of those using the PDF and or CDF. And so essentially what we can do with these statistics is we can see whether or not x is less than or equal to a certain value, if it is greater than a certain value, or if it's within a range. So and that sort of allows us to see all the different types of probabilities that we can compute, that we would be interested in computing for a normal random variable. So I'm going to give you a little bit more to play with here, because I want to sort of draw it out. So this is an example of a normal random variable, and it's a fairly good assumption on my part that most of you have seen this type of curve, so the normal curve. And essentially, what we can do is we can say that this represents A, this represents B, and the probabilities that we're computing, because this represents a probability density function of the normal random variable, we can essentially compute the probabilities by taking the area under the curve, which is essentially just integrating the PDF. So for example, anything, if we want to compute, let's say, the probability of x being less than or equal to A, what we would do is essentially compute the area under the curve here. And firstly, let's say we wanted to see the probability of x being greater than B, then we could compute this area under the curve. And let's say we also want to see the range, so we could also calculate the range from A to B, the probability of the range from A to B. And let me just change the pen color here so you can see it better. And that would essentially be this area under the curve. So again, for the normal distribution, for the normal probability distribution using the probability density function for the normal random variable, the probability is just the area under the probability density curve. The other option is we can also compute it using the cumulative distribution function. And the cumulative distribution function doesn't exist with using a closed form, or doesn't exist as a closed form in practice. So as a result, there's no easy formula to determine what these specifically are. So typically we have to go in and actually look up these values, which we can do using through standardizing our random variables, or we can also use other statistical or computational tools such as spreadsheets, etc., or other statistical software. But basically, because we understand because we have the utility of a probability density function and the cumulative distribution function, we can compute areas and ultimately get at probabilities. And we can also sort of do the inverse of that, and we can compute x if we know what a certain probability is. And those are things that we're going to cover this week. So why is it that normal probability distributions are the most common? And the reason is because of the central limit theorem, which we are also going to cover. And essentially the central limit theorem says that a sum or average of a large number of random variables has an approximate normal distribution regardless of the distribution of individual random variables. So it sort of allows us to see that if we have if we know that that random variables typically have a normal distribution, and as such we can essentially extrapolate and make assumptions because other random variables share a similar or share a normal distribution as well. And because of that, it allows us for things like hypothesis testing. And this is something we will cover in week 3, but essentially it allows us to make comparisons between different random variables. So with that, that's what we're going to cover for week 2, and I hope you have a better idea of the important things that we're going to cover, and specifically related to binomial random variables and normal random variables, and then also the central limit theorem.